So, hi everyone to this new lecture on scheduling. This is actually one of my favorite lectures and one of my favorite topics. It's quite dear to my heart, if I may say. This is basically work that I work with on a daily basis, and I think it's very exciting. Let me start by actually telling you that we have actually started most of the basic building blocks that you would need to build your own operating system. We have covered most of the required data structures. We have, or the popular data structures. What comes next, it will be mostly basically putting things together, trying to show how the whole system works together in different parts. There will be, of course, new stuff every lecture, but that's another thing. So why is scheduling important, and why do I think everyone should care about how scheduling is done? Suppose that you go to a supermarket and you stand and you look at the different queues to basically pick where to stand in order to put your pay your stuff. So if you don't have one of these fancy machines, then you will have to stand in a queue, and you'll have to take a decision on which queue you're going to stand in, and that queue can be basically very long or very short, and you might make your decision based on the length of the queue. But this is not the whole story, because you might have a queue that has just one person in front of you, and that person has just bought half of what ICA has, so he has like 10,000 items or something, and you definitely do not want to stand in that queue. But you might make the decision based on just some very superficial looks of how the queue looks like, and just go and stand there and get stuck. So this is why scheduling is important. I mean, it can save you time. And if you look at if you start working for one of the larger companies, if you become a CEO, or if you even do not work for one of the larger companies, you just have a family, then time is actually money, or simply a cost for you. So that performance of you basically being served fast, if you spend half an hour just standing in that line doing absolutely nothing, it's half an hour from your life. Well, you're going to die anyway, and then that's half an hour from whatever time you have on Earth, right? So you're paying in some sense. And one thing to note also is that you might try to solve the optimization problem by basically going through each queue in the supermarket, looking at everyone's shopping cart, counting the number of items that person has. And if you have in a larger ICA or in a larger Coop, for example, if you're at Coop forum and there are like maybe 15-20 people paying at the same time, each one having on average 20 items, then you will have to count for 100 items, and you will have to start thinking about, okay, how long does it take to, for example, for the cashier to weigh apples and see the weight. And I mean, you will reach eventually an optimal solution, and that will be basically, okay, I should stand in that queue, but by the time you reach that solution, you would have already basically gone, the whole state of the system would have changed, so people will have come, and then basically your solution is completely useless, because although you know that you should have stood in that queue, but that queue has just gotten 3 new customers, and now you need to redo everything to solve the optimization problem. So a super optimal solution that comes in too late is probably worse than you standing in the worst queue of them all, right, in the supermarket. So you might have even spent more time calculating which queue to stand in, which cashier queue to stand in, versus the time, more than the time you would have if you stood in the worst queue. So in that sense, you have to always think that this is a very important thing. And as we have discussed in one of the lectures, performance can be measured in different ways. One of them is response time or delay, basically, and that's basically the user perceived time until his task is done, and that would include everything from the time that the user sends a request till the time he basically leaves. And if you have seen, there was an animation movie which I can't remember. This Zootopia. Yes, Zootopia. If you have seen Zootopia, there were sloths standing, like basically serving people, right? And your response time will include the response time of interacting with the sloth. So if you basically go on the in a supermarket where sloth is your cashier, well, that will add to your overall experience, right? It will be that slow. Okay, so response time is everything, including your queuing time and the time that the sloth takes to serve you. Then there's predictability, which is basically you want, as a supermarket manager, you basically want low variance in response time for everyone, right? So if you have a customer, if you have 100 customers who buy 20 items, you want to basically have cashiers, people working in your supermarket, who will serve these 20 customers with almost equal time. I mean, it can be a few seconds more or a few seconds less, but the huge variability is really bad. So because it also adds to the experience of some of your customers. You don't want your customers, if you have 100 of them, you do not want to lose 5 of them because you have a really slow cashier, for example. Then there's throughput. As again, a supermarket manager, you want to serve as many customers per hour as you can. And if you have, suppose that you have an infinite number of customers coming in, and they will, I mean, your limits would be basically the time when you start in the morning and the time when you close at the evening or at night. Okay, so this is your limit. So you want to serve as many customers as you can during that period, because that's basically the amount of profit that you're going to make. There is the scheduling overhead, and that's basically if you have if there's a time between two customers in your supermarket, if there's a long time, because your cashier basically drinks and goes to the toilet every time your customer is done. So you'll have long scheduling overheads, and these can really reduce the overall performance of the system in terms of both throughput and response time. So you might want to measure that. Then there's fairness, which is basically you want all customers to feel that they have been treated fairly. And that's a really hard thing to define. It's also again a measure of how much response time that the customer gets, or also it might be that your customer gets the same or the treatment that he requires. So if a customer basically needs needs to buy milk, he should be able to buy milk and pay for it, and if a customer needs to buy apples, then he should be able to buy the apples and pay for it also without really losing anything. And then there's starvation, and that would be the problem of you basically for example, saying that I have a policy that any customer who comes with less than 10 items will be his orders will be processed faster, for example. So suppose you go to a restaurant that basically has a policy that says that if you order one thing, we bring it to you in 5 minutes, but if you order 10 things at the restaurant, then you will have to wait because we have to serve the people who order one thing and basically in 5 minutes time. And that would basically mean that you might, if there are an infinite number of people who order things that take 5 minutes to prepare, then you as a customer who orders 10 things will just starve because you will not be able to eat. So of course a major problem in general when recording video is that I do not hear myself until I am done recording, and apparently I had the microphone amplifying my sound too much, so I hope I'll put a note so that I hope that I'll even say in the email that the first part of the lecture is extremely loud because it hurt my ears. Okay, so what we will try to cover basically, or what we will cover, is that we are going to talk about scheduling for multiple environments. Tomorrow's lecture in class we will talk a bit about some queuing theory. This is a very mathematical discipline, so I actually prefer to have it outside of the lecture, outside of the video lecture. And then there's we'll talk a bit about overload management and a case study also again tomorrow in the lecture. In this video lecture, we'll basically cover scheduling for multiple environments and different scheduling algorithms, and we'll take a deeper look at how scheduling is done in the kernel, with of course code snippets. So we will cover the whole chapter 7 as a whole, so you should basically read the whole chapter. So scheduling. Let's start before talking about what scheduling is to talk about what a workload is. And the workload is basically a set of tasks, jobs, threads, processes that need to run on the processor, or that need to access to some resource. Basically, it's typically the processor. But it can be the I/O devices also. The workload description includes not just the number of tasks, but also when does the task arrive, because that can make a difference. Two tasks arriving in opposite order, reversing order, can make a huge difference in how you do the scheduling. And how long or how many cores or cycles does it need to compute whatever it is supposed to do, not cores but cycles, because each task will have its own profile, basically requiring some resources different from other tasks. We would like to build a scheduler that works for multiple applications and multiple environments, not just a single application nor a single environment. So not just right now you have implemented your syscall. Some of you have showed me the results on both the ARM processors, which you have in the Raspberry Pi and the Raspberry Pi 3s, but also some of you have shown me their code in virtual machines and on desktops. There are things that you need to consider when building a scheduler. Is that the workload can be either compute bound, so it can be basically in deep need of memory, deep need of CPU. Sorry, it can be memory bound, which basically means that you have to communicate a lot with memory. Typically, you might also need to communicate with the disk, but that's different. And I/O bound. And I/O bound in the book and in many operating systems book, they include memory bound applications because they need input output from outside of the CPU. But when you talk about softwares in general, I/O bound typically means that you need to access disk or access something that is outside of the memory architecture too. There is also the notion of network bounded softwares, but these are again can fall within the I/O bound application category, but they are applications that basically, like BitTorrent for example, that needs to download a lot of things from the internet. So a scheduler is called work conserving when basically the scheduler output never makes the processor idle when there is work to do. So of course, if there is no work to do, if there is nothing to do, then the processor will be idle because, well, there is nothing to do. But if there is anything to do, then the processor should not be idle as long as there is more stuff to do. So I've been trying to get this sound to be correct and not so noisy for the past 15 minutes. I hope this time it works. I've played with a few settings and I hope it works. So as I was saying, that scheduling will be work conserving when there are no left jobs in the queue. Basically,
the processor can be idle, but otherwise the processor should be doing stuff. So let's look at some of the most famous and most useful scheduling algorithms that you will find not just in operating systems but in almost all systems, including cloud systems and um, parallel computing systems and HPC, and yeah, they are everywhere. The first scheduling algorithm is first in first out schedulers, and the second one that we are going to look at right now is shortest job first schedulers. And let's start by FIFO, first in first out. And it's quite simple. Suppose that you have 5 tasks that arrive with a few microseconds between them. So let's think of task 1 that is running right now as as it has arrived at microsecond 0, task 2 at microsecond 1, task 3 at microsecond 2, and so on. Then FIFO will just schedule the tasks on the processor, will give the tasks processor time in the order they came, no matter how long they will take, and not looking at anything more than their arrival time. So it's quite simple, and as you see, this is basically its output. It will look like this. Shortest job first, also sometimes called shortest remaining time first, which is actually a more accurate term, because a shortest remaining time first scheduler will basically look at all tasks in the queue waiting for processor time, and pick the task that has the least possible time of running until completion, basically, and then run it until completion. So suppose that you have a task that would take 1 hour, but it has been running for most of the time and only 1 minute remains out of it, and then 3 other tasks that are each 2 minutes. Then shortest job first, or shortest remaining time first, will run the 1 hour job, will schedule the 1 hour job first because it's going to finish earlier than the other the shorter jobs. Although the shorter jobs have shorter total runtime, but the remaining runtime is longer. And in that case, suppose in our previous example, then SJF will just start scheduling things based on how long they will take. SJF or SRTF, they are both equal in one. I mean, they are synonymous. Uh, so SJF is quite theoretical for operating systems, because in an operating system there is no way that you would know how long a process will take or a thread will take before completion. But it has found its way, although it's very theoretical for operating systems. It's actually one of the most used algorithms in systems such as, for example, high performance computing systems like the HPC2N supercomputer we have at UMIU, where you basically might run it. I mean, you're not, they are probably not running SJF because it's a bad idea for other reasons, as we will see. But you can possibly run it, because in that case, basically, when I'm running my experiment, I basically tell them that, well, I need 10 processors, 100 gigabytes for the next 10 minutes, and someone else says that I need 10 processor, 2 terabytes for the next 2 days, and then it's basically clear which one has shorter time and also shorter compute capacity requirements. So let me ask you a couple of questions. When would you use FIFO scheduler? Okay, now that you have answered that, hopefully correctly, if you look at the figure, 2 slides before this figure, what is the average response time for FIFO and what is the average response time for SJF? So, given what you see over here, hopefully you got that right also. But let's basically say, when do you use FIFOs? FIFOs are very good in the sense that they minimize scheduling overheads. You absolutely do the you do the preemption. You basically move from one task to the other once the first one is done. So I mean, it's the absolute minimum number of scheduling decisions that you need to make. You just need to basically have a queue that tasks get registered to it with their arrival time, and then basically start them in sequence. It's also quite suitable for compute intensive applications when most of the applications or all of them would require the processor for an equal amount of time. Because otherwise, uh, if you look at, for example, this example, I mean, FIFO here is not perfect because you have a compute intensive application that takes the processor for this much long time, and then the others short what tasks that could have finished very early were blocked. But suppose that all of your tasks are actually as long as the first one, then it doesn't really make sense to play them or start them in different order, right? Because I mean, the first one will always take the same time as the second one as the third one. So um, there is no point in trying to uh, rearrange them using their running time. So it's quite suitable for compute intensive applications. If you have an application that will just run and use the CPU for a few seconds, and all your applications are like that, then FIFO might work. Then let me ask you a question. Why would you use the shortest job first? So shortest job first has been proven to reduce the average response time. While the if you look at this figure, I mean, the average response time for the for this system is basically a combination of if oops is basically a combination of the time from, I mean, you start counting basically from the time you schedule the first task until it finishes. And then for task 2 in the FIFO case, it starts also, I mean, suppose that they arrived almost at the same time, maybe 1 millisecond later, 1 nanosecond later. Then it starts roughly at the same time when the first task got scheduled. It just happened to arrive a bit earlier, very slightly earlier, and then it ends basically when the second task finishes its processing. So you have just added an overhead of the total runtime of the first task, and this overhead you will add to all your four tasks that come after the first task. While in SJF, what you would do is that there will be no added overhead for the shorter tasks except for the time required to run the short task, which is pretty minimal. So T2 will be I mean T2 right now. T finishing 2, the time required to finish task 2 is equal to T1 plus T processing 2, right? But in the second case, in SBF, it will be T processing 2 only. And for task 3, it will be T processing 2 plus T processing 3, and these are short. So they basically are pretty fast. And then when you do take the average, then it will be reduced. The scheduler basically uh, will preempt the longer one for the shorter one. For an SJF, if you basically stick by the SJF philosophy, and you have a task that is running that will take 10 hours, and then a task comes in that will take 10 milliseconds, then you would basically preempt the long running task into for the sake of the shorter running task. And this makes me ask you another question. What could go wrong? Okay, the one thing to note is, as I said, is that what counts is what remains, right? Uh, One thing to also note is that SJF is very bad for response time variance because it highly depends on how many tasks you are getting from each type. And what could go wrong? It's starvation basically. If you have a few longer running tasks, and then if you have 100 long running tasks or something, and you have thousands of these short running tasks, like millions of them, then you'll keep scheduling the short running ones until you're done with them, while the long running ones might just wait forever indefinitely, as long as you have short running tasks. And this will just kill performance because you'll be starving the long running tasks, and you will have a very long tail latency. And in most cases, we are talking about processor time. So I mean, 100 millisecond is basically norm. I mean, is the normal time you would allocate to a task. So, I mean, you might have a task that ends up finishing in 10 minutes, which is just crazy and acceptable. Okay, so these two have their merits, but then there is also round robin, and round robin is well, a nice way to schedule tasks. And the way you would do it is that you would basically divide the task into time slices, sometimes called quantum, time quanta, and basically you will run each task for its slice. So that slice can be, for example, let's say 1 millisecond. So you run the task one for 1 millisecond, but the remaining part of task one has to wait. And then task 2 for 1 millisecond, task 3 for 1 millisecond, task 4 for 1 millisecond, task 5 for 1 millisecond, and then you start again with task 1 for 1 millisecond. Now, this can be useful to some extent. This can be viewed as a midway between FIFO and SJF in some situations. But you typically don't. I mean, there are multiple trade-offs here. Before we talk about the trade-offs, let me just ask you, why would you use round robin? Well, you would use it because it will basically always provide you with fairness. It will also provide you with the almost never the your tasks will never starve because they will eventually get time on the processor, and that's basically these are the merits of round robin. And can you think of how to make round robin behave like FIFO? So basically, round robin can behave like FIFO if you have a very long time quanta over here. Okay, so if your time quanta is absolutely is absurdly long. Let's say that you have a time quanta of 1 minute, and most processes will finish in a few milliseconds. Then basically, what will happen is that it will converge to round robin. It will just operate on things at the time by the time they come, based on the time they come. So round robin is not always the best solution for every single problem. So let's look at this example. For example, suppose you have tasks that look like the lower figure, and well, it looks like this basically. They're all equal in size, but they are pretty long also. If you run FIFO or SJF, it doesn't really matter. Both of them will yield the same result because all tasks are equal in length. So SJF will basically find no shorter task to run, and it will just run things based on the time they arrived in because that's the way they are ordered basically. So it will look just like a FIFO. And if you operate with round robin, that basically means that you will have to define. I mean, for the time you would have finished task one, you will divide it on the five tasks, with each one of them getting 1/5 of that time. And then by the time you have finished the second task, you have still finished zero tasks using round robin, but you have divided the second time to five quantas, also given them to each task. I mean, allocated each one of them to each task, and you would go on like this. So by the time here you have finished four tasks, you have finished here zero tasks, and basically your average response time is almost as bad as all. I mean, it's quite bad. It's equal to the total time of running each of these requests on its own. And that's your average response time, and you typically want your average response time to be low. I mean, in this case, for example, your average response time will be half of this response time. So in that case, round robin is actually a bad idea because it will basically reduce the total average response time. It will not hurt your tail response time, but it will reduce the overall system uh, the overall system quality of service. So let's talk about what is best, for example, when you have a mixed workload of I/O and CPU. And I/O intensive workloads, they typically have shorter CPU time. They do not require a lot of CPU time, but they require response responsive responsiveness responsiveness from the operating system. Because, for example, an I/O bound application is something like the text editor you use, or your programming environment that you use Vim or or Eclipse or something. And if you look at this, they basically have to wait for you until you type. But once you type, you would want it to appear on the screen. You do not want there to be delays between you typing and the text appearing on the screen. And if the editor is sluggish, you will be pretty unhappy with the performance. And there are a lot of these applications that basically have this characteristic of being I/O bounded, waiting for some input from some I/O device, and once the input is there, you would want to basically run it as fast as possible. Some other applications are CPU bound; they will just run on your processor for the coming 3 hours. So if you are into the simulation business, for example, and you are simulating a power plant, and the power plant will simulation typically would take a few days. Then if it takes a few days and 1 hour, it will not. I mean, if it takes basically 72 hours or 73 hours or 71 hours, you wouldn't really care, right? I mean, you wouldn't. It doesn't matter. So you typically want your I/O bounded applications to be served as fast as possible, and they typically require very little CPU time. There are very few applications which can block on both CPU, or which can basically have be both CPU bounded and I/O bounded at the same time, right? Because any I/O operation will basically mean that you're going out of the processor, and if you're going outside the processor, then you might be dealing even with mechanical parts, and these are pretty damn slow for a processor, which basically makes almost I/O bounded applications very lightly using the CPU. So if you have a system that looks like this, you have some I/O bounded applications and some CPU bounded application. The question that all schedulers try to answer is how can you operate such that you provide both the I/O bounded applications and the CPU bounded application, the notion of fairness. And the notion of fairness is really hard to actually quantify, but you can think of it as, I mean, basically, in the case of the CPU bounded versus the I/O bounded application, uh, well, the I/O bounded application will need the CPU at any time, and it might need it a couple of times, basically in very short period, but then go and get blocked for a very long time. And in that case, would it be fair to make the I/O bounded application wait because it's not its turn on the processor, and keep the CPU bounded application running forever? Because that would basically mean that, well, your fairness is kind of skewed a bit, okay? Because you are in some sense giving preferential treatment to the CPU bounded application, because most of the time when the IO bounded application is scheduled, or I mean its turn comes basically on the CPU, it will not be able to use the CPU because it's, well, stopping for IO input still, so it just cannot run now. It's unrunnable. So, and now you have passed its turn and give the processor to the CPU bounded application. Now it's again the turn of the CPU bounded application, and then the IO bounded application can basically remain for very long periods of time blocked, doing nothing, because it required the CPU for a few milliseconds, but you didn't release the CPU because it was not its turn. So the concept of fairness is really hard to quantify, and it's something that is in almost all schedulers try to apply some notion of fairness. And this is also important because you might try to game the scheduler by basically having a process, an application that just starts 100 threads, while you have another application that just has one thread. And these are competing applications, right? I mean, yes, they are running on your computer, but at the same time, each software developer has the complete. I mean, he really wants you to think that his software is kicks ass, right? It's really fast. It's blazing fast. I've never started that piece of software and had any trouble. But then if the way the software developer is doing that is by basically starting 1,000 threads, thus acquiring a lot of resources unproportional to what is required by actually the application he has developed, then this will be a problem because it will starve all other applications. You might even start thinking that why is that application not really performing well? And in operating systems and in a lot of other systems, the way that fairness is imposed is using max-min fairness. And max-min fairness is a nice concept that basically says that you try to maximize the minimum allocation given to a particular process until all resources are assigned. I.e., if you have a process that has not taken enough CPU time, you would just assign it CPU time until it has uh, basically used the equal amount of CPU time to any other process without looking at its turn. And that would also apply for IO bounded applications. So suppose you have a CPU bounded application that uses the IO for very few cycles, basically, not cycles, but for very few milliseconds. It basically requires IO from some for some operations and midway before it finishes the operation. In that case, you would apply also the max mean fairness give the give uh, the CPU bounded application some time on the I/O devices. So you try to maximize the minimum allocation given to a particular process until its resources are until basically it has resources at the same level uh, of the other uh, processes. And yeah, is there anything here that I have not said? And of course, I mean maximum fairness with round robin would always give you some sense of maximum fairness if you have very short cycle times, basically. Sorry, quantas. So if you have very short time slices, then you can basically have maximum fairness protocol using just round robin. So now that we have talked about fairness, let us talk about how operating systems actually try to achieve such fairness. And the way that Linux, for example, do it is using a version of what is called a multi-level feedback queue. And a multi-level feedback queue is basically, sorry, designed to try to achieve everything at the same time, which basically means that it achieves nothing optimally. So it is designed basically to try to achieve the responsiveness of shortest job first, and that's basically by trying to run short tasks very quickly. It tries to achieve low overhead that FIFO has and minimize the time spent making scheduling decision. It tries to achieve starvation freedom, which is a property that you find in round robin. And it tries to achieve that fairness in the system and using the maximum fair share of the processor. And it tries to also have the idea of background tasks which should not interfere with user work. So background tasks such as memory cleanup. I mean, in theory, for example, the Java garbage collector should be one of these background tasks, but in practice it is not. So this is what it tries to achieve. And if you try to achieve everything, you probably do not achieve anything optimally. Basically, master of every jack of everything. That yeah, jack of everything, master of nothing. Of nothing. So an MFQ basically works like this. You have round robin queues, and these queues are have different priorities. So you have multiple queues within each one. You work with priorities, but in each queue you work with round robin, and basically you always schedule things from the highest priority queues first, followed by basically things from lower priority queues in sequence. But then when doing that, you do not basically wait until you finish everything in the higher priority queue, but you rather use these priorities as weights, and that would basically means that you would try to run some tasks from the first queue, high priority queue, but also some tasks from the last priority queue. And for each priority queue would basically have a different time slice for its round robin, because you're in round robin you have the quanta, you have the time slice for which your processor runs without any interruptions, and these would be different for different priority queues. So for short running jobs, for example, 10 milliseconds might suffice, and therefore you might have 10 milliseconds for your very highest priority queue, and that would be basically sufficient for IO intensive applications that just need the operating system very fast, but then would just release it after a few milliseconds. But then for longer priority queues, for higher priority queues, you would have a higher time slice. And that's the theory. We'll look at how Linux implements it in a very short while. So in summary, to summarize how things are done in a unit processor, basically, you have trade-offs like everything. You have FIFO that minimizes overhead, but can result in very poor average response time. It also has some notion of fairness. I arrived first, so I finished first. But it also has some notion of unfairness because, well, you arrived first, but then you blocked the CPU for 10 hours. So uh, it's problematic. If tasks are equal in size, FIFO is optimal in terms of the average response time. And considering only the processor, SJF is generally optimal in terms of average response time. So just looking at the processor, shortest job first will give you almost always the best average response time, but one of the worst tail response times that you can think of. Therefore, you get very bad variance in response time. If tasks are variable in size, then round robin might help you a bit. It approximates an SJF, but then the best way to do it would be to use an MFQ, for example. If tasks are equal in size, then round robin will have very poor average response time because everything roughly finishes almost at the same time. So it's very bad in that sense. And then if you have tasks that intermix between processor and IO, then you can benefit a lot by having SJF, but round robin might be a very bad idea because in that case you will have the application having to wait for 100 milliseconds, basically doing nothing, because it's round now. Well, it just needs 1 millisecond. Maximum fairness can improve response time for IO bounded tasks. So if you implement some form of maximum fairness, this should basically improve your overall performance in terms of response time if you have IO bounded tasks. And it avoids starvation because there will always be sort of a quota for. I mean, you will always try to equalize for different processors, for different processes. Sorry. Okay, and then the MFQ is a way to basically improve the overall system performance and try to basically be to be jack of everything but master of nothing, basically. So for multiprocessor scheduling, I mean, all what we have been talking about is for uniprocessors. You have a single processor core, and you run on that, and you're trying to schedule things on that processor. But for multiprocessor scheduling, can you, for example, use a centralized MFQ with locking? And again, an MFQ is something that looks like this. So can you use an MFQ with locking? No. And the reason is that you will end up with contention for the schedulers using for the scheduler spin lock. You'll have basically with an increased number of processes, MFQ will basically have contention when it comes to the scheduler spin lock, because you will need, all of them will need to call the scheduler basically. You will have cache slowdown. I mean, this is for a centralized MFQ, as I said. So you have a single scheduler queue and everybody's trying to access it. And there will be cache slowdowns because, well, you'll have the ready list data structure basically pinging from one CPU to another, and also values pinging from one CPU to another. There will be very limited cache reuse, so caching will be hurt significantly. And then the solution is, of course, to have a pair processor data structure and use still MFQ, but then rebalance only when it makes sense. So you'll have an MFQ per processor basically, and as long as each MFQ has some jobs to run, some tasks to run, you will not try to rebalance. You will only try to trigger a rebalance when you end up in situations where one of the queues ends up really overloaded and the other one ends up lightly loaded or with no load at all. As all applications are basically can basically have multiple threads that run together trying to do something, right? So an application can be multi-threaded and can have 10 threads, and basically it runs them to completion basically, and these threads will result, I mean, they will join, merge, fork, and merge, and I mean yield, and they interact in some way. Okay, so then you're faced with a question, since you have now different MFQs for different cores, which is how to schedule the threads, because how do you schedule threads from the same application, for example? Okay, and the easiest way is basically to be completely oblivious about it, basically never think that applications are multi-threaded, and just start having them scheduled without the scheduler knowing anything about how they interact together. This can be a solution, but what could go wrong with such a solution? So there will be bulk synchronization delays. That's the first problem in this solution. As some of you might have predicted, what could go wrong is that you will have delays due to synchronization, for example. So bulk synchronization delays. In a typical multi-threaded program, you will not have all threads having the same amount of computations, and you might have them even running on, I mean, they will be running on different processors, and as they are running on different processors, they will probably also run at different speeds, because each processor will have its own MFQ, and by processor here I mean CPU core, and since each one of them has its own MFQ, you will end up with basically the variable load depending on where you end up. And if you are running in such an environment, then the threads basically will have when they do thread join, for example, if they all join at some point, they will have to wait for the slowest thread before the program can proceed, right? Because you, for example, suppose that they have divided a matrix multiplication, for example, they're doing matrix multiplication, and they divided the matrix onto 16 different threads.
So bulk synchronization delays will basically mean that you will be as slow as your slowest thread, and that thread can be because it's processing more data, or it can be just because, well, but tough luck, you just ended up in the wrong queue. And this will be also manifested if you have a producer-consumer model. So if suppose that you're, for example, feeding a buffer with some input, and some other threads are reading from that buffer,
the output to process the output, for example. Then in the producer consumer model, if you have such if you have oblivious scheduling, then you might end up basically having delays in your producer consumer model, because the whole scheduler is completely oblivious on what it should run before, which threads should run basically first, in terms of because you have these chained threads basically. It can be also that the critical path will be delayed, and the critical path is parts of the code on which everything else will depend. So if you have delays in your critical path, you will end up with significant delays everywhere in your system. And you might have preemption of lock holders also, because as the scheduler is completely oblivious on which threads belong to which applications, then a thread can acquire a lock on a much needed resource and basically get preempted, because it's round robin in MFQ and in the same priority, and it will get evicted because of other threads in need of or other threads time slice starting, and it just gets evicted while holding the lock, and the other threads cannot proceed because you have a lock being held by a process that is waiting, by a thread that is waiting in the waiting queue. So these are all manifestations of what could go wrong if you have oblivious scheduling. So the way that most people would actually handle, for example, threaded multi applications on most operating systems. Threaded multi-threaded applications on a multi-processor machine, on a multi-core machine, is that you will use what is called gang scheduling, and you will basically try to schedule the same task at the same time everywhere. And there might be some issues with gang scheduling, because if you have, for example, single-threaded processes, their performance might get hurt by basically having gang scheduling running on occupying all cores, while single-threaded processes do not really run. There is also the law of diminishing returns, basically. So if you have an application that has very limited parallelism, then adding more processors will not really improve your performance. And this is, if you look at the curves on the left hand side, then the lower curve basically tells you that no matter how many processors you will add, you will not get really an improve in response time. There are perfectly parallel processes, and these are very hard to write and almost non-existent in nature. Not in nature, but rather in most the programs that we write, basically. And in that case, you will basically gain linear gains by adding more processors to the system. But there is also some applications that might benefit from extra processors until some level, and this is the law of diminishing returns. And in that case, you would basically want to work or to parallelize, as long as parallelism gives you linear or almost linear performance increases. You'll get losses maybe in the order of 5 or 10%, but you can't tolerate that because you'll get a boost of 60%. But if you're adding an extra processor, so instead of running in just one core, you're running now on 2 cores, and speed up you're getting is 10%, then that's basically useless. Okay. When you are also, most most operating systems, when it comes to thread preemption of lock holders, for example, they would also implement a mechanism such that the processor will actually a process that starts and finds that from, for example, higher from higher priority job that starts and finds out that I cannot proceed because a thread from a lower priority queue acquired the lock. I mean, then what would happen is that the operating system will basically delegate the priority by basically running the low priority thread that acquired the lock and slept was preempted until it releases the lock, and then basically stop the lower priority thread and rerun the higher priority thread. And there's also scheduler activations that can basically provide the applications with upcalls to make the application aware that there's now a possibility for the application to improve its scheduling. Okay, last thing I'm going to talk about before talking about how or one of the last things that I'm going to talk about before we jump into how the Linux scheduler is actually built is energy aware scheduling. And basically I'm not going to go into the details of how energy aware scheduling is done, but I'm just going to put a few notes on how people consider these problems. And the problem is that basically on laptops, for example, or on mobile phones, your scheduling will affect how much energy you're basically using from the battery. And if so, and that's something that you can actually see in some between different mobile phones and between different, for example, if you upgrade between different operating system versions, so different Android versions or different iOS versions or different Windows versions on your mobile phone, this can actually affect your energy consumption if you have gone through that. And energy consumption, energy aware scheduling is basically now being handled by different means. The first one is basically in the processor design itself. So the processor provides the scheduler with capabilities to reduce the energy consumed in the system. One of these is the dynamic voltage and frequency scaling mechanism, DVFS. And dynamic voltage and frequency scaling basically reduces, I mean, if there is not too much load on your system, on your laptop or on your mobile phone, then it will clock down your processor. And if it clocks down the processor, so if the processor is supposed to run at 3 gigahertz, for example, it can clock it down to 1 gigahertz or lower, and then what you will get is basically a significant reduction in the amount of power or energy you're drawing from the battery. There is a more recent technique that is more fine grains, that is called RAPL, and RAPL is you can actually try it on almost all computers since 2000 and all processors since 2011 roughly, and it provides you with a mechanism, or provides the either you through an API, or it provides also the operating system with a mechanism to basically say that I want to run at 10 watts now, or something like that. And there are other trends, for example, like using ARM cores, or what is called wimpy cores sometimes. So ARM cores are called wimpy cores, and wimpy cores typically use significantly less power compared to other processors like Intel processors. And this is why, for example, you have now the Intel Atom, and you have a few of these processors that are really simple and really weak, but really energy efficient. And this is why most mobiles run on ARM processors, because they are just very power efficient. Then, given the processor design, the scheduler can do some changes using the primitives that were provided by the processor, such as shutting down some parts of the computer, shutting down, for example, a memory bus, or shutting down you can't even shut parts of your processor on some processor designs. Most new processors will allow you to do this. And when you think about, for example, that the new Intel Xeons Broadwell they are no longer just a processor, but they come with an FPGA, a field programmable gate array, so that you can program also the hardware. And you might want to look what an FPGA is if you do not know what an FPGA is. Then you might even shut the FPGA, you might shut a coprocessor, you might shut down the GPU, and so on. And you might also start shutting down other resources, like for example your Wi-Fi, or on your mobile your cell phone network interface, which is actually quite typical that your mobile phone does. It actually when there is good coverage in the area, then your mobile phone will sleep basically for a while. The cell phone network adapter interface will basically sleep for a while. Well, a few milliseconds is a while, or a few seconds. I mean, if it's a second even, you wouldn't notice. And every some predefined time, it will wake up, send a beacon signal, send a signal basically to the mobile tower, telling it, "Oh, I'm alive," and then the mobile tower will reply. So real-time scheduling, and we'll talk quite a bit more about real-time scheduling in the Linux kernel. And these are basically softwares that you would use for example, for controlling aeroplanes, right? I mean, you have an operating system on an aeroplane, on a Saab, for example. On the Saabs that are owned by Bra Aviation, we actually had once a lecture by some of the people who build these these airplanes, and it's just an operating system. They have an operating system running on their airplanes, and I mean on both military and non-military planes, you will have these real-time schedulers basically to make sure that the plane flies. You also have some operating systems in your car. For example, recent BMW or recent Mercedes, recent Volvo will have hundreds of computers that will run a distributed operating system typically. So you would need, I mean, you wouldn't want your anti-lock braking system or your anti-skid system to basically be preempted because right now your radio is going to fire up or something while you're going to slide into the lake, right? Similarly, even your movie on the computer, I mean, if you're playing a movie on the computer, I mean, you want real time. I mean, if the video is rendered too slowly for you to see, then you would basically have a very bad quality of experience, which is I mean, you'll have jitter and you'll start seeing breaks in your video. You might even start seeing the pixels in the video in a bad way. And similarly, if you're playing Half-Life and you shoot an enemy, then your fired shot, you do not want it to, like, the effect to appear 5 seconds later, because, well, that's just meaningless. So real-time scheduling, you will always have some real time, you'll have some deadline that you want your scheduler to meet, okay? And to meet that schedule, to meet that deadline, the scheduler typically does one of three things. The first one is to over provision, basically have a bit of extra resources almost always to be able to run at any time you ask for real-time task to be scheduled. The second one is basically to try to do scheduling based on earliest deadline first. So if you know that, well, the shot in Half-Life for a human player to be able to understand that, to feel the difference, we need, for example, I mean, the shot effect should take less than 200 milliseconds. Then you basically know that this is the time span during which you can compute everything and run everything and show things on the screen to the human, okay? And you can have something that's called priority donation to circumvent priority inversion. So if you have the multi-locking, some application that holds a lock that you would need for your real-time schedule, you might do priority donation, basically give it higher priority to release the lock, and then take it back to basically make sure that your deadline is met by making sure that nobody holds the locks that you need.